The last clip spoke about energy and the principal quantum number, and this clip is going to talk about total angular momentum. And L, the total angular momentum quantum number. Before we talk about L and total angular momentum, which also goes by capital L, I should explain a little bit about what the concept of angular momentum is. And I'm going to explain the concept in terms of waves. So, we had before that for linear momentum, P, in terms of a wave, P equals h over lambda. Here's the wave. Here's the lambda, and it's the lambda going in a line, in a straight line. So you have a wave going in a straight line. It's going in a certain direction. That makes the momentum the linear momentum. The angular momentum goes by L, and L is going to have the same kind of relationship, but H for a lambda going in a circle. So here is a circle, and then we put a wave on it, and from here to here, this is lambda in a circle. So, and angular momentum is the momentum of spinning. So a hurricane has a huge angular momentum because it's spinning very fast. Linear momentum is how much you're going in a straight direction. Angular momentum is how much you're spinning. And in terms of waves, they're controlled by then the linear wave motion or the circular wave motion. Okay, so that's what angular momentum is. And now we can get to L, the total angular momentum quantum number. And it turns out that the total angular momentum quantum number is determined by the letters. The P letter, the S letter, and the D letter. And I can put it right here. When L equals, here, I'll put it right here. S equals, for S, P, D, and F, L, which is the total angular momentum quantum number, is 0, 1, 2, and 3. And the relationship is when L is small, capital L is small. I'm not going to give you the exact formula. Capital L is the total angular momentum. When L is big, capital L is big. So little l, the total angular momentum quantum number, measures the total angular momentum. And the main point of this clip is to show that the fact that S, P, D, and F have different angular momentum, total angular momentum quantum numbers is actually contained in the pictures. And let's take a look at those pictures. We're going to look at the y function. Here's the S, the y function. The P function. And at the D function. And the question we're going to ask is, how far does it take to go through from one wave back to itself? And remember, a wave goes back, you see, it's positive over here, and it's positive over here. It's how much it takes to go from positive to positive, from crest to crest. That's the wavelength. So here, that is a lambda in a circle because we're going from plus to plus in the wave. There's another lambda in a circle. And so the wavelength in this case for the 3D is 1/2 the circle circumference. Here, it's positive, it goes negative, it takes all the way here. Put in chat for the p orbital. What is the length of lambda in terms of the circle circumference? How many circle circumferences does it take to come all the way back from positive to positive? Put it in chat. And the answer is it takes 1 circle circumference. So these pictures, the 1 circle circumference, the lambda's 1/2 circle circumference, come from understanding the shapes of the orbitals. And now we're going to compare it to the statement about the total angular momentum. The total angular momentum is inversely proportional to lambda going in a circle. Lambda going in a circle is how many times bigger is lambda going in a circle for P versus D? This is the P state, this is the D state. How many times for lambda going in a circle is lambda for P bigger than D? Put it in chat. And the answer is it is twice as big, the lambda. Therefore, the angular momentum, which is inversely proportional for P, should be what fraction of that of D? I'll say it again. Lambda for P is twice as big as lambda for D. It takes, because it's twice, it takes 1 full circle versus half a circle for lambda in a circle. Therefore, L for P should be what compared to D? Well, if it's inversely proportional, put it in chat. If it's inversely proportional and for P, lambda is twice as long, L has to be half as big. And that's exactly what we see here. The L quantum number is 1/2 of that for P versus D, and it is entirely due to the fact, it's entirely understandable in terms of the pictures of the orbitals and the fact that it's the wavelength going in a circle which controls angular momentum.